The more you explore the world, the more you will realize that signs are everywhere. They give us directions. They help us communicate. They warn us of danger. Signs in the sky can be used to help us navigate and even predict the weather. Some signs need no words at all. Hello, fellow mathematicians. My name is Dr. Masullo, and I'm here today to speak to you about signs. No, not these signs. I'm talking about these signs. Sign numbers. What do they mean? How do we operate with them? So grab your papers and pencils and join me today as we learn about signs. We'll be right back after this bonus question. Hello, math wizards. Check out this magic square problem. Here we have a 3x3 grid. That means we have 9 blocks in which to fill. And we're also given the numbers 1 through 9. If I was to ask you to place those numbers in the box in such a way that when we add vertically, horizontally, or even diagonally, we would get the same sum. You think you could do it? Does it sound kind of tricky? Challenging perhaps, but not impossible. Let me give you a clue. I'm going to tell you that the magic sum we're looking for is 15. That means when we place the numbers in the blocks and we add either vertically, horizontally, or even diagonally, we should get a sum of 15 in every possible direction. Does it still sound tricky? Well, here's one more clue. What if I told you the center square contained the number 5? That's a really big hint, because now we can see that the numbers on either side of the 5 have to pick up the remaining 10 in order to get a total of 15. Here's what I mean. If I grab a 7 and place it up above, I would need to grab a 3 and place it down below. 7 and 3 gives us 10. Plus the 5 makes 15. So we have a sum of 15 down the center column. Can we do that again? If I was to place a 9 to the left of the 5, I would need a 1 to the right of the 5, because 9 and 1 also makes 10, plus the 5 in the middle to make the 15. What about the remaining 4 squares? Let's see what we can do. If I was to place a 2 in the upper diagonal, I would need an 8 in the lower diagonal. Again, 8 and 2 to make 15. We only have 2 squares left. If I was to place a 6 in the upper right-hand corner and a 4 in the lower left-hand corner, I would also make the 10 plus 5 to get 15. Take a moment and check it out. Does it make 15 in every possible direction? While you're thinking about it, think about other ways that you could arrange the numbers, and also think about more challenging magic squares. And for those history buffs out there, did you know that Benjamin Franklin constructed a magic square with 8 by 8 dimensions? He did that back in 1750. So do a little research on the magic square. You won't be disappointed. And now, back to our show. So what are signed numbers? Well, signed numbers, or integers as they are otherwise known, are basically positive and negative whole numbers. We can use them to count on a number line, or even a coordinate plane. Signed numbers can show us temperatures above and below zero. We can use them to express a distance below sea level, or to show deposits and withdrawals to an account, and even as a way of demonstrating the loss or gain of yardage on a field. Working with signed numbers can be a challenging topic, but we're going to use an analogy here using the phrases happy and not happy to symbolize a positive number and a negative number respectively. For our example, happy would be positive and not happy would be the opposite, and that would be a negative number. So if I was to say something like not happy, that would be equivalent to being happy again, because we're saying the opposite of not happy is happy. Now let's try to apply that to an actual real-life example. If we had $100 in the bank, that would be a positive number, a positive $100. But putting a negative sign in front of that $100 means we owe the bank $100. So now let's see if we can see some kind of pattern here. A negative in front of a negative is saying the opposite of negative 100, which is now a positive number again. When we have one negative symbol in front of the number, our answer comes out negative. Two negatives back to back, we're saying the opposite of negative is back to positive. Here we have three negatives. Do you start to see the pattern now? The opposite of negative is positive, and the opposite once more brings it back to negative. So hopefully you're starting to see the pattern forming. Every time we have an odd amount of negatives, like 1, 3, 5, 7 negatives, for example, the answer is always going to come out negative. But when we have an even amount of negatives, like 2, 4, 6, etc., the answer will be positive. And if you take a note down here, odd number of negatives, the answer comes out negative. Even number of negatives, the result will be positive. And now, back to our show. The handshake problem, a classic problem for mathematicians. Here's how it goes. When two people meet, they shake hands. That consists of one greeting. But what if there were more people in the room? Let's say there were 20 people in the room, and each person had to introduce themselves to every other person. You could see how quickly this could become a very complex problem. Let's take a closer look. Okay, so let's see if we can figure out this handshake question. On the left side of the board, I have the possible number of people in the room, in this case from 1 to maximum of 20. On the right-hand side of the board, we'll put the number of handshakes that occur, or the number of greetings appropriate for that number of people in the room. When there's one person in the room, there's no one else to greet. They can't shake their own hand. So 0 handshakes would occur. If 2 people are in the room, they would each greet each other, and that would be 1 handshake occurring. 3 people in the room will look something like this. 1, 2, 3 handshakes occur. 4 people in the room one, 2, 3, 4, 5, 6 handshakes occur. Let's try one more. 5 people in the room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 handshakes in the room. Now you can see it gets progressively more difficult to draw this. So what we're going to try to do is look for a pattern. We have 0, 1, 3, 6, 10. Do you see a pattern forming here? Well, when I look at this, I see a jump of +1, then +2, then +3, then +4, and so on. If we kept that pattern up, what would happen as we work our way down to 20 people? Let's try that. Plus 5 would be 15 handshakes for 6 people in the room. Plus 6 would be 21 handshakes for 7 people. Plus 7 would be 28 handshakes for 8 people. Plus 8 would be 36 handshakes for 9 people. Plus 9 would be 45 handshakes for 10 people. Plus 10 would be 55 handshakes for 11 people. Plus 11 would be 66 handshakes for 12 people. Plus 12 would be 78 handshakes for 13 people. Plus 13 would be 91 handshakes. Plus 14, 105. Plus 15, 120. Plus 16, 136. Plus 17, 153, plus 18, 171, plus 19, 190. And now, back to our show. Now here's a chance for some guided practice. Let's see if you remember what we learned. The first question asks us to simplify. We have a negative, a positive, a negative, and another negative in front of our number 34. But our skill here is to count how many negatives we have. That's going to determine our answer. I count 1, 2, 3 negatives. That's an odd amount of negatives, so our answer should be negative. If you selected choice A, you were correct. Here's another example. Negative 8 times negative 4. Remember what we learned. We're going to temporarily disregard the negative and multiply 8 times 4, which is 32. Then we're going to go back and count the number of negatives. 1, 2. That's an even amount, so our answer should be positive. If you said positive 32, you were correct. Let's see if you know what you're doing with this one. Negative 7 times 2. We're going to temporarily ignore that negative and multiply 7 times 2, which is 14. Once again, go back and count how many negatives you have. I see only 1 this time. That's an odd amount, so our answer should be negative. If you selected negative 14, you are correct. Here we have negative 4 times negative 2 times negative 3. I read it as 4 times 2 times 3. 4 times 2 is 8, and 8 times 3 is 24. Go back and count your negatives. 1, 2, 3. Odd amount, negative answer. Here's a division example. Negative 18 divided by negative 6. So we'll think in our heads 18 divided by 6 is 3. Go back and count your negatives. 1, 2. Even amount, answer should be positive. Simplify negative 20 divided by 4. We think 20 divided by 4 is 5. 1 negative, odd amount, answer should be negative. Slightly more complex question here. We're going to work on our numerator first. We'll say 6 times 3 is 18. Then we'll divide by our denominator, 9. So 18 divided by 9 is 2. Go back and count your negatives. 1, 2, 3. Odd amount, answer should be negative. And now for a word problem. George owes 5 people each $4. How would you write this in symbolic terms? Well, there might be more than one way. If we owe 5 people $4, The fact that we owe them $4 puts us in the negative zone. So each person is getting $4 from us, so from our perspective, that's a negative 4. And we're doing this 5 times. So 5 times negative 4 would be one way to write it. Also, we could treat each person as receiving 4 from us, so that would be a negative 4 written 5 times. So if you chose B and also C, those would be the 2 correct answers. We'll be right back after this bonus question. Ever watch how people climb stairs? If they're carrying a heavy backpack or briefcase, they might go up 1 step at a time. But if they're in a hurry, they might skip 2 steps at a time. Well, here we have the staircase problem. This staircase has 10 steps. If you could only climb it using 1 step or 2 steps at a time, or combinations of both, that means 1s and 2s, how many ways would there be to climb the 10-step staircase? Let's take a closer look. Here we have the staircase problem. The question's asking us to figure out how many ways there are to climb a 10-step staircase, only being able to take 1 step or 2 steps or combinations of 1s and 2s at a time. It's going to be a pretty daunting task to keep track of all those numbers. How are we going to know if we counted them all? How are we going to know if we missed any? How are we going to know if we repeated ourselves? Well, like any of these challenge questions, it's always easier to start with a smaller problem first and look for a pattern and build our way up. So on the left side of this chart, I have the number of steps possible from 1 to 10 inclusive. And on the right side of the chart, we're going to keep track of how many ways there are to climb those steps. Let's see if we can look for a pattern. If there's 1 step, there would only be 1 way to climb it. 2 steps, we would just do 1 plus 1, or skip the 2 steps, so that's 2 ways to climb it. If there were 3 steps, we could do 1 plus 1 plus 1, 2 plus 1, or the reverse, 1 plus 2, giving us 3 ways to climb it. Now, at this point, you might be saying to yourself, well, if there's 1 step, that's 1 way to climb it. 2 steps, 2 ways. 3 steps, 3 ways. 4 steps would be 4 ways. Well, let's take a look. With 4 steps, we could do straight 1s. We could do 2 plus 2. 2 plus 1 plus 1. 1 plus 1 plus 2. Or 1 plus 2 plus 1. That's 1, 2, 3, 4, 5 different ways to climb the steps. Now you'll see that our pattern, what we suspected, has taken a turn. Let's try one more. 5 steps. Again, we'll start with straight 1s. 2 plus 2 plus 1. Reverse that. 1 plus 2 plus 2. 2 plus 1 plus 2. 1, 1, 1, 2. Reverse that. 2, 1, 1, 1. We also could do 1 plus 1 plus 2 plus 1. Reverse that. 1 plus 2 plus 1 plus 1. And that's 8 different ways. Now you can see it's getting progressively harder to list all of these. So let's take a pause and see if we can spot a pattern. 1, 2, 3, 5, 8. Did you notice 1 plus 2 is 3? and 2 plus 3 is 5, and 3 plus 5 is 8. Let's continue. 5 plus 8 is 13. 8 plus 13 is 21. 13 and 21 is 34. 21 and 34 is 55. And 34 and 55 is 89. So that's 89 different ways to climb a 10-step staircase, only taking 1 or 2 steps at a time. There's a name for this pattern, and it's called the Fibonacci sequence. Do a little research on Fibonacci and check it out. And now, back to our show. Okay, we made it through simplifying, multiplying, and dividing with the signed numbers. Now we're going to enter into a new topic, and that's adding and subtracting. So, I don't want you to forget your rules that you learned so far with multiplying, dividing, and simplifying, but I need you to know that this is a different set of rules that applies here, and I don't want you to mix the two up. Okay, we have on the board here a couple of examples of adding and subtracting with the signed numbers. Take a look at our first one. Positive 4 plus a positive 6. Both numbers are positive, so there's really no thinking involved here. We just simply add them together. A 4 plus a 6 is a 10. What happens when we have negative numbers or even subtracting numbers? Well, for starters, we can interchange a subtraction symbol and a negative symbol. They pretty much do the same job. So when I see negative 4 minus 6, I say to myself, well, I don't really want to learn a new set of rules for a subtraction problem. So what I'll do is, I'll take that subtraction, make it into an addition, as long as I change the sign of the following number. So now I would read it as negative 4 plus a negative 6. And then I would say to myself, I lost 4, I lost 6, same signs, we just sum them up. A loss of 4 and a loss of 6 is an overall loss of 10. So we would read it back as a negative 10 answer. So let's make a notation there. When the signs are the same, we sum them. So I'm going to write same, sign, sum. And that should be easy to remember because it all starts with the letter S. Same, sign, sum. Take a look at this third example. Positive 4 minus a 6. Again, I don't have to think of a separate rule for subtraction. I can change that subtraction problem into addition as long as I change the sign of the following number. So now I'm going to read it as 4 plus a negative 6. Well, if the signs are different, meaning a positive 4 and a negative 6, the signs are different, well then we have to take the difference. The difference from 4 to 6 on a number line is a 2. But which one was further from 0? In other words, which one had the greater absolute value? Well, the negative 6 is further from 0. The negative 6 has the greater absolute value. And the number with the greater absolute value dictates the sign of your answer. So if this guy was a negative 6, our answer would be negative. So what I'm going to write here is different signs we take the difference. And just remember, the number with the greater absolute value determines the sign of our answer. Here's a more complex problem below. We have negative 13 minus negative 4 plus 17 minus 45. Lots going on here. First of all, I notice I have the two negatives back to back. Now we learned this earlier that the opposite of a negative is a positive. So I can treat that as a positive 4 instead of minus a negative. So that's for starters, we make that adjustment there. I still have a lot going on. I have a negative 13, a now positive 4, a positive 17, and a negative 45. I think it would be easier if we took those numbers and put them into teams. Here's what I mean. I'm going to make a positive team and a negative team. On the positive team, I have the 4, the 17. On the negative team, I have the 13 and the 45. Now, the commutative property allows us to rearrange the order, so what I did there was totally legitimate. Now we're going to focus on the positive team. A 17 and a 4 gives us 21 on the positive side. A negative 13 and a negative 45 gives us a negative 58 on the negative side of the board. So now we look at it and we say, okay, I have a positive 21 and a negative 58. Different signs, we go to our rule here, different signs takes the difference. The difference between a 21 and a negative 58 is a difference of 37. But the question is, which one's got the greater absolute value? Which one's further from 0? Well, the 58 is further from 0. So that's why our answer would be negative. We'll be right back after this bonus question. The school club problem. Once school begins, students will be deciding what extracurricular activities they want to try. Students are involved in soccer, student council, math club, and basketball in a ratio of 6 to 3 to 2 to 4, respectively. There are 180 students eligible for one of these activities. For the purpose of this problem, no single student is involved in more than one activity, and everyone is involved in something. Based on this ratio, how many students are involved in the math club? Here's what our chart should look like, and now let's take a closer look. It's giving us a ratio of students involved in the clubs as 6 to 3 to 2 to 4. That doesn't mean there's actually 6 students involved in soccer, 3 in student council, 2 in math club, and 4 in basketball. The term ratio means for every 6 in the soccer, there are 3 in student council, 2 in math, and 4 in basketball, respectively. Our goal is to figure out how many students are actually involved in each club. Well, we were given a clue. There are 180 students total, and each student is only involved in one and only one club. I know in the real world you could be involved in more than one club, or you could be involved in none of the clubs, but then the problem would take on a whole other level of difficulty. For the sake of this problem, we're going to keep it simple. So there's a total of 180 students. So we need to see what is the scale factor that is involved for each of these clubs. If we were to add it as it is, 6 plus 3 is 9, plus 2 is 11, plus 4 is 15. So how many sets of 15 are in 180? Let's check it out. 15 divides into 180. 12 times. So our scale factor is 12. That means for every 6 in our ratio, we have to multiply by 12 to get the actual number of 72 students in soccer. In the student council, 3 times scale factor of 12 gives us 36 on the student council. 2 times a factor of 12 gives us 24 in the math club. And 4 times a factor of 12 gives us 48 involved in basketball. If we were to add 72, 36, 24, and 48, that would be our total 180 students. But the question specified how many are in the math club, so we really only need to be concerned about the 24. That's our answer. And now, back to our show. Complex complex problems. For example, negative 13 minus a negative 4 plus 17 minus 45. There's a lot going on there. So for starters, what I'd like to do is take care of this double negative back to back and change it to plus a positive. So now it would read negative 13 plus 4 plus 17 minus 45. There's still a lot going on there. So what I'm going to do is I'm going to make two teams, a positive team and a negative team, and see if we can sort this thing out. On the positive team, I now have the 4 and the 17. On the negative side, I have a negative 13 and a negative 45. Okay, the commutative property says that we could rearrange the order of the numbers, so we're okay there. That's legitimate what we've just done. What I want to do now is add up what's on the positive side. 4 and 17 gives me a total of 21 on the positive side. Negative 13 and negative 45, same sign sum, once again, gives us a total of negative 58 on the negative side. Now we're faced with different signs. 21 on the positive side, negative 58 on the negative side. And when the signs are different, we must take the difference or subtract. Now the difference between a 21 and a 58 is a 37. But we have to say which of our numbers carries the greater absolute value. In this case, the 58 is further from 0. Therefore, our answer is going to be negative. Let's try one more. Here we have 48 minus negative 8 plus 7 minus negative 12 minus 3. First order of business, let's take care of our double negatives. We have two sets this time, so whenever we see a double negative, we know we need to change it to positive, and then we're going to organize our teams. We'll have a positive team and a negative team. On the positive team, we have 48, 8, 7, and 12. On the negative team, we have only the negative 3. We add up our positive side for a total of 75. Our negative side, again, only has a negative 3. The signs are different, so we take the difference. 75 minus the 3 is a 72, but since our 75 is further from 0, our answer is positive. Here's some guided practice. The directions here say to simplify 8 minus 13. We said before that any subtraction problem can be turned into addition simply by changing the sign of the following number. So I will write this as 8 plus a negative 13. And then we revert to our rules. The signs are different, so we will take the difference. The difference between 8 and 13 is 5. But then ask yourself, which number is further from 0? Or which number has the greater absolute value? In this case, the 13. The 13 is carrying a negative symbol, so our answer is going to be negative. Here's a really nice question, because all of our numbers are carrying the same sign. And we said before the rule is same sign sum. So we simply have to add all of these together. 7 plus 4 is 11, plus 3 is 14, plus 2 is 16. They're all negative, so we just keep the same sign. A great one to use our team approach. We have some negative numbers and we have some positive numbers. So let's set up our teams. Who's on the positive team? 4 and 7. Who's on our negative team? Negative 8 and negative 9. On the positive side, 7 and 4 is 11. On the negative side, negative 8 and negative 9 is negative 17. The signs are different, so we must take the difference. The difference between 11 and 17 on the number line is 6, but the 17 is further from 0, so our answer must be negative. We're starting to get a little more complex now as the expressions get lengthier, but we know our rules, so we're going to first take care of our double negatives, and then we'll build our teams. Once again, on the positive team, we now have a 7, we have a 10, and another 7. On the negative team, we have a negative 10, a negative 6, and a negative 3. Now, here's a tip. If you have the same number on the positive side as you do on the negative side, they will cancel each other out. Think about that for a second. 10 and a minus 10 is a 0. So if it helps you to eliminate those, please do so. Let's see what's left. On the positive side, 7 and 7 is 14. On the negative side, negative 6 and negative 3 is negative 9. Signs are different, once again, so we take the difference. The difference between 9 and 14 is 5. The 14 is further from 0, so our answer is positive. Negative 6 plus 9 minus 7 minus 5 plus 11 minus 2. Let's once again build our teams. Positive side, negative side. On the positive side, we have a 9 and an 11. On the negative side, we have a negative 6, a negative 7, a negative 5, and a negative 2. Here's a tip, just like we did before. If we can find anything to cancel out on the positive and negative side, let's take advantage of that. So I'm looking at this negative side, and I see 7 and 2, both negative. A negative 7 and a negative 2 is a combined negative 9, which would neutralize our positive 9. So let's eliminate that right now. I also noticed a negative 6 and a negative 5, which is a combined negative 11, which would cancel out our positive 11. So there's nothing left on either side. So we have a sum total of 0. And now for a word problem. Sarah owes $30 on her credit card. She uses the card to buy an $80 dress and eat a $20 lunch. She returns a pair of shoes and gets a $40 credit. Finally, she pays $25 on her account. What is her account balance? I can't think of a better use of our team approach than this word problem right here. So what we'll do is we'll set up, once again, a positive and negative side. Owing $30, that would be a negative. Buying the $80 dress, that would also land on the negative side. The $20 lunch, another negative. Returning the shoes to get the credit, that would go on the positive side. And paying off $20 on her account would also go on the positive side. Let's see what we have on each side. On the positive side, 40 plus 25 is 65. On the negative side, 20, 80, 30, that's a negative 130. The signs are different, so we take the difference. The difference from 65 to 130 is a difference of 65. But the 130 is further from 0, and it's carrying the negative. So our answer is negative 65. So we interpret that, in this case, as owing the $65. We'll be right back after this bonus question. The students at your school are having a Friendship Gram card sale as a fundraiser. They have 1,000 cards to sell. In order to be ready for the customers, they want to have the cards in the envelopes organized in such a way that a customer can ask for any quantity of cards between 1 and 1,000 inclusive, and the students would be able to give that exact number simply by handing the customer a certain combination of preloaded envelopes. They will mark the outside of the envelopes as to how many cards they contain, but they will not be able to add or subtract cards from the envelopes once they are inside. Please mark the envelopes below to show how they should be set up and explain any pattern you discover. And here's a hint: their pattern will break at the last envelope due to the 1,000 card limit. And now, let's take a closer look. The question asked us to fill in the envelopes in such a way that we could create any number by adding up the number of cards that are inside the envelope. The least amount of cards a customer could ask for would be 1. So we know we need an envelope that's carrying 1 card inside. The next question we have to answer is, what's the next amount the customer could ask for? Well, that's obvious. It's got to be 2. But we have to make a decision. Do I put another single card inside this envelope and hand them both envelopes for a total of 2 cards? Or do I put 2 cards in this envelope? Well, the better choice is to put 2 cards in this envelope, because if you're thinking ahead, not only could you make 1, but you could also make 2, and handing both cards, you can also create the number 3 if the customer wanted 3 cards, which brings us up to the next number we need to cover, which is 4. And again, we have a decision to make. Should I put 1 card in this envelope? That would total up to 4. Should I put 2 cards in this envelope and give them 2 plus 2, which also totals up to 4? Should I put 3 cards in here and give them 1 plus 3, which also totals up to 4? Or should I have a card standing by itself containing 4 cards in the envelope? The answer is, the best choice is to put 4 cards in the envelope, because again, thinking ahead, we can not only create 1, 2, 3, 4, but I can do 4 plus 1 to make 5, 4 plus 2 to make 6, and if you add all 3 envelopes at this point, we can make up to 7 cards at this point with giving all 3 envelopes. Now, if you pause for a minute, you can see we're covered up to 7, and we also have a pattern going here. Each time I go to the next envelope, I'm doubling the amount of cards located inside. 1 times 2 is 2, 2 times 2 is 4. If you continue your pattern, 4 times 2 would be 8. 8 times 2 would be 16, 32, 64, 128, 256. Now, if we were to continue the pattern, the next envelope would contain 512. But if you remember the directions, the hint was that the last envelope will break the rule. And the reason is, we're only dealing with 1,000 cards total. So if you add up the number of cards that we have at this moment, we are covered up to 511 cards, which leaves a difference of 489 cards, which must go in the last envelope. And now, back to our show. Your skills with signed numbers, you will be able to simplify more complex expressions and even solve some algebraic equations. So now, let's take a look at some of the signs of things to come. Here we're asked to simplify an expression. So let's apply some of the rules that we learned. Inside the parentheses, we have 16 plus a negative 12. The signs are different, so we'll take the difference. The difference is 4, and since the 16 is further from 0, the 4 remains positive. Here we have 7 minus 10, which we could turn into 7 plus a negative 10, so that we can apply the same rules. The signs are different, so we once again take the difference. The difference is 3, but since the 10 is further from 0, it gets a negative 3. All that's left is to multiply the results. 4 times negative 3, and we get 12. One negative is an odd amount of negatives, so our answer stays negative 12. Working inside the parentheses again, we have 9 minus 20, which we could turn to 9 plus a negative 20. So now you see the signs are different. We'll take the difference. The difference is 11, but since the 20 is further from 0, it gets a negative 11. In the right-hand side, parentheses, we have a negative 3 plus a negative 4. The signs are the same, so we remember the rule. Same sign sum gets a negative 7. Now we're going to multiply negative 11 times negative 7. So we'll temporarily ignore the signs and do 11 times 7 is 77. Then go back and count how many negatives there are. 2 negatives is an even amount, so our answer becomes positive. Now here's a chance to solve an equation. X plus 18 equals 10. If we subtract 18, in order to isolate the x, we must do it to the other side as well. So now we have 10 minus an 18. If we do the scratch work on the side, 10 minus 18 can be rewritten as 10 plus a negative 18. Now you can see that the signs are different, so we will take the difference being 8, but since the 18 is further from 0, our answer becomes negative 8. Here's another one to solve. In order to isolate that x, we must add 19 to both sides. So now we can have negative 12 plus 19. The signs are different, so we take the difference. The difference is 7, and since the 19 is further from 0, our answer stays positive. X minus 30 equals negative 42. We'll add 30 to both sides in order to balance this equation. We have a negative 42 and a positive 30. The signs are different, so we will take the difference. And since the negative 42 is further from 0, our answer becomes negative. Here's another. N minus 18 equals negative 9. In order to isolate the n, we'll add 18 to both sides. A negative 9 and a plus 18. The signs are different, so we'll take the difference. Since the 18 is further from 0, our answer stays positive. This equation involves simplifying before we can solve it. On the left-hand side, I have a plus 6 and a negative 15. The signs are different, so I will take the difference. The difference is 9. But since the 15 has a greater absolute value, that makes it a negative 9, which we can treat as a minus 9. Okay, bringing down all our terms. In order to isolate the c, I must now add 9 to both sides of the equation. On the right-hand side, I have 25 plus 9. Same sign sum gives us a total of 34. Okay, here we have a two-step equation. For starters, let's get rid of the 23 by adding it to the other side. Bring down our terms that are remaining. On the right-hand side, I have a negative 55 and a plus 23. The signs are different, so I will take the difference. But since the 55 carries the greater absolute value, that makes a negative 32. The last step would be to get rid of the 4 by dividing, and that leaves us with n equals 8. And once again, we have a single negative, so an odd number of negatives makes our answer negative. Negative 16 equals 12x minus 76. Another two-step equation. We'll start by adding 76 to the other side. On the left-hand side, the signs are different, so we will once again take the difference. And since the 76 is further from 0 and it's carrying the positive, that leaves us a positive 60 equals 12x. One more step would be to get rid of the 12 by dividing both sides by 12. 60 divided by 12 is 5. Try one more. Negative 30 equals negative 3x minus 72. In order to get rid of a minus 72, we must add it to both sides. A negative 30 and a plus 72. The signs are different, so we must take the difference. And since the 72 is further from 0, we have a positive 42 to bring down. Okay, one more step, and that's dividing by a negative 3. So 42 divided by 3 would be 14, but one negative is an odd amount of negatives, makes our answer negative 14.